So let's talk about what's become a very popular technique in generative AI, retrieval augmented generation, or RAG for short, or as I like to call it, cheat to win. Let me talk about why. So RAG is kind of like an open book exam for large language models for your generative AI models. And I didn't make that up. They've been calling it that from the get-go. The idea is that you're going to query some external database for the answers and give that to your large learning model as part of the prompt or part of the process of generating its response. So in a way, it's cheating. You're looking up the correct answer from some external data source and injecting that into the generation of the actual response. So you're not really relying on the underlying model itself, except for really just how to reword what you've given it for information, right? So let's take a look at this example on the right here. Let's say I'm asking my chatbot, what did the president say in his speech yesterday? Well, we all know that most large learning models like GPT and whatnot have only been trained up to a certain date in the past, right? So they typically don't have up-to-the-date knowledge. Let's imagine, though, that we pass that into RAG, like my little picture of a RAG there. So let's say that it goes off to a database that's kept updated every day of the latest news articles. I could query that database and say, hey, do you have any articles about the president giving a speech yesterday on a given date? Maybe it comes back with some sort of a match that's relevant to those parameters to that query. And we get that back and we just stick that in the query before we pass it on to the actual generative AI model. So then we can sort of frame that query, sort of reformat it using a template and say something like, what did the president say in his speech yesterday? Consider the text of the following news article in your response, and then paste in the text that you got back from the database. And if you phrase that the right way, ChatGPT or whatever you're using can use that to generate a response that takes that information into account. So it's a way of incorporating external data that may be more up to date or even proprietary that you didn't have before, but it's kind of cheating. You're kind of making a glorified search engine here, right? So let's talk about the pros and cons of RAG. What's it good at and what are some of the downsides of it? Well, the big upside, the pro column here, is that it's faster and cheaper for incorporating new or proprietary information compared to fine-tuning. So we looked at fine-tuning earlier and had an example of that. It took hours and hours and hours for that to happen, right? So it was also pretty expensive. In comparison, though, using RAG can cost less than a penny. We're going to do an example at the end of this lecture, actually, where we do that same thing where we did with fine-tuning to recreate the character of Data from Star Trek, but we're going to do it using RAG instead of fine-tuning. And literally, it costs less than a cent to do it. So economically, it's very attractive. And if you're a company trying to implement this stuff and push out some innovative AI model that takes your own company's information into account, it's a very tempting way to go about it. Updating information is simple. You just have to update the database that you're pulling that information from, right? So you don't have to go back and retrain anything. You just update your database and that gets injected into the system as it's generating responses. Now, the real benefit of RAG that's promoted most widely is that it's a potential solution to the hallucination problem. So when you go and talk to an AI enthusiast and you say, yeah, generative AI is great, but it lies a lot, they say, oh, but we have RAG. You can use that to actually inject trusted data into your responses and prevent that problem of it telling you incorrect information. Well, yes and no. So if you are going to ask it about something that it wasn't trained on, a good model will just say, hey, I don't know the answer. You know, you're asking me about something that happened after my training cutoff, right? But sometimes it will just make stuff up. And if you're giving it a source of information that's better than making stuff up, maybe on the whole that's better. So, okay, yes. It can help, but it's not a solution to the problem. It's not going to completely prevent hallucinations wholesale. If your boss says, I want AI search, this is a really easy way to do it because basically you're just taking a search engine and wrapping it with AI, right? That's how RAG works. You're going off and querying a database, searching a database for some answer, and feeding it to a generative language model to give it a more human response, right? Also, keep in mind that technically you're not training a model with this data with RAG. So if you're using some sort of proprietary information where there might be restrictions about how you use it, you can say with a straight face that you're not actually using that data to train an AI model. And well, there might be political consequences to doing that, right? On the con side, though, you have now created the world's most complicated search engine, right? You've taken this very straightforward search to a database, which we've been able to do for decades, right? And you've wrapped it with this incredibly complicated generative AI system. Why? You know, maybe you don't even need to do that. Maybe you're better off just giving those search results right back to you, right? I've seen one example, for example, where they use RAG to produce product recommendations. And they do that by querying this big graph database for getting recommendations that were pre-computed using traditional methods. And all they're doing with the AI part of it is just rephrasing that into natural language. Why? Just present back the product recommendations as is. You don't need to take on that extra complexity and that extra expense necessarily. So do ask yourself if you're overcomplicating things by using RAG. Also, it's going to be very sensitive to the prompt template that you use to incorporate your data. So the way you ask it to incorporate that data can really influence the results that you get. So just based on the wording, when I was playing around with it, if I worded things the wrong way, it just parroted back those search results exactly verbatim as is. It didn't even try to rephrase them or incorporate information from the underlying model into the response. So you do have to experiment with how you're phrasing your prompt to say, take this data into account. By the way, that's not the only way to do it. We'll talk about that in a minute. There are some slightly more principled ways of handling RAG than just modifying the prompt. But either way, you're going to need a prompt to tell the underlying model how to use this data. And because of that, it's non-deterministic. So let's say that there is a new version of the model that rolls out that was trained on different data or trained in a different way. Maybe the way it reacts to that prompt will change over time as a result. That's kind of a scary thing, right? Like if the underlying model changes, the results that you might get from RAG could just stop working entirely for all you know. And it can still hallucinate. Like I said, it's not a general solution to the hallucination problem. It's going to be very dependent on the relevancy of the information you're retrieving, right? So if your retrieval from that database is not giving you highly relevant results, it could still result in hallucinations or giving you misinformation, right? It's only going to be as good as that data that you're pulling from that retrieval stage. So keep that in mind. Again, it's not a panacea. It's not a complete answer to the hallucination problem. So let's take a look at a specific example here. Let's say I want to build a chatbot that's really good at answering questions from the TV game show Jeopardy. So if you remember Jeopardy, the idea is that you give it an answer and you have to give the question, right? So in this case, the answer is, in 1986, Mexico scored as the first country to host this international sports competition twice. So how could I use RAG to go answer that if that's not something that the underlying GPT or whatever it is knows about? Well, that's where our retriever module comes in. So we pass that raw query into our query encoder. Its job is to expand on that query and incorporate data from our external retrieval. So let's say I have a database of every Jeopardy answer and question that's out there from all time. I can query that database for that answer and come back with a list of the most relevant questions that are associated with that answer, right? So I'm going to get back a list of documents sorted by relevance for that query. And I can then incorporate those into the query itself and rephrase that query to say, in 1986, Mexico scored as the first country to host this international sports competition twice. Please take into account the following known question: what is the World Cup? And that gets passed into the generator, which just gives you back a nice natural language response that basically says, what is the World Cup? So that's an example of RAG. Again, it's pretty simple to wrap your head around. All we're doing is querying some external database of some sort, taking the results and working that into the query before we pass it on into the generator. That's it. So basically, we're just handing the generator potential answers from an external database. We're giving it the answers. That's why I call it akin to an open book exam. So how do you pick a database? There's many ways of going about that. What are you going to query in that retrieval stage? Well, you can use whatever's appropriate for the type of data that you're retrieving. So I talked earlier about that example of retrieving product recommendations. For that, maybe a graph database is the most appropriate choice, something like Neo4j. Or if you're just doing traditional text search, you can just use something like Elasticsearch that will give you back relevant text matches based on whatever you're searching for, just using TF-IDF, term frequency and inverse document frequency. We talked about that earlier in the course, or anything along those lines. You can also often sort of manipulate these search engines into being something else, but I'll talk about that in a bit. Another approach, though, is instead of just doing a prompt injection like that, you can also do something a little bit more principled. So you can use the Tools API and the OpenAI API, for example, and use that to try to get GPT to provide structured queries to inject into your actual modified query, right? So they have an example online called RAG with a graph database. And that's one example of how to do this. There's a link here if you want to go check it out. But that's what this stuff on the right here is doing. So basically, we start off by saying, okay, chatbot, okay, OpenAI, here is some general rules on how to create structured data requests from a given question that I see. So if I give it this really long system prompt that says, look for these kinds of words, look for these types of things in the question, and I want you to structure it in this way, you can actually get it to actually create structured data like this. So for example, if someone says, which pink items are suitable for children, it might be able to automatically produce this structured little JSON snippet that says color pink, age group children. So if you give it enough specific instructions, it can actually structure that for you. And then if you're using the Tools API, which we talked about a little bit earlier in OpenAI, for example, you could actually have that passed back into a function that OpenAI uses when generating the actual response. So it's a little bit more complicated than just modifying the prompt, a little bit more structured, but still you're depending on that system query to make sure that it knows how to construct this structured data accurately. And it's a little bit more complicated, not necessarily better. However, for some reason, when you go and look for examples of retrieval augmented generation online, usually you find people using something called a vector database. So let's talk about what a vector database is. Now, before we talk about vector databases, let's first review what embeddings are. And you'll see why this is relevant. An embedding is just a big vector associated with your data, right? So that's why we're talking about vector databases here. Embeddings are vectors. So you can think of an embedding as a point in this multi-dimensional space. And in practice, that's usually hundreds or even thousands of dimensions, where everything is sort of positioned based on its similarity to other things. So embedding vectors, which are, hundreds or thousands of dimensions in size, are computed such that items that are similar to each other are close to each other within that higher dimensional space. So to let you wrap your head around it again, imagine that we have a two-dimensional embedding here, where we just have X and Y axes, because we can visualize that on a screen here. Maybe the words potato and rhubarb are going to be close together in those spaces, and that embedding vector would just be the vector from the origin to where those are in this space. However, for example, stuff about science fiction like the Starship Enterprise, Spaceballs, the Orville, maybe those are all clustered somewhere else, right? But they're still going to be close together because they have a certain similarity to each other, right? Now, the good thing is that embeddings can be very easily computed if you're doing machine learning language stuff already, right? So you already need to deal with embeddings if you're creating any sort of deep learning natural language model. So often you can just use existing tools at hand to compute these embeddings and make it easy. So OpenAI, for example, has an embeddings API that we looked at earlier, and we can use that to compute a bunch of embeddings all together at once at extremely low cost and quite quickly as well. So once you have these embedding vectors for everything, you just got to stick them somewhere. So let's put them in a vector database, shall we? All a vector database does is store your data alongside their computed embedding vectors. And that gives you a very easy way to search for things that are similar to the thing that you are searching for. Again, you can leverage the same embedding system that you might already have for your larger system, which makes things a little bit easier. Retrieval is going to be take a couple of steps. So if there's something you want to search for, find something similar for, first you need to compute an embedding vector for it. And then you will query the vector database for the top items that are close to that vector. So basically we're doing k nearest neighbor in this multidimensional embedding space to get back the top n most similar things. We call that vector search. That's all it is. It sounds fancy, and honestly, I think a lot of this terminology and fancy talk is just to help sort of legitimize what's kind of cheating, like I talked about, but it works, so I'm not going to criticize it too much. Now, there are different vector databases out there you can use. Like I mentioned briefly, you can coerce a lot of existing databases to do vector search that weren't necessarily designed for it originally. So there are ways of using Elasticsearch, traditional SQL relational databases, Neptune, Redis, MongoDB, Cassandra, many others to do embedding, to do vector searches just by structuring things the right way. But there's also purpose-built vector databases out there as well. On the commercial web service side, we have things like Pinecone and Weaviate. And if you go search for examples of using RAG online, most of them use those services. I kind of think they might be getting a kickback from them. There's also open source solutions as well, though, like Chroma, Marco, Vespa, Qdrant, LanceDB, Milvus, and more recently VectorDB. That's a very simple little Python module that we're going to use in our example shortly. So let's talk about that example. Let's say that I want to create data from Star Trek, but this time instead of using fine-tuning and actually building up a fine-tuned model that really sort of mimics the brain of data, if you will, this time we're going to cheat and we're just going to use RAG. So how might that work? Let's say a user types in a prompt, data, tell me about your daughter Lal. So how might that work with RAG? So first we need to compute an embedding vector for that query. Data, tell me about your daughter Lal. And we'll get some sort of, multi-dimensional vector that says where this sits in our embedding space. We can then do a vector search in our vector database that's been pre-populated with everything that data ever said before, right? So just like we did before with the fine-tuning API, we have a document that we built up of every line of dialogue that data ever said. And we can stuff that into a vector database offline. That involves looking up, in batch manner, every embedding vector that's associated with every script line. So offline, I have this script that looks at everything data ever said, computes the embedding vector for that line, and stuffs it in this vector database. And that's faster than you might think and cheaper than you might think too. Again, when I did this for real, using all 200 episodes or whatever it is, it still cost me less than 1 cent in US dollars to do all of that, multiple times, mind you. So very fast and very inexpensive to populate that data. But when we do that vector search for our query, data tell me about your daughter Lal, it's going to give me back the top however many similar lines I want to see, right? Maybe it's the top 10, whatever it is. That will give me back the most similar dialogue lines that talk about Data's daughter Lal. And how you make that relevance work, again, is key to the performance of a RAG system. So that quality of those results, the relevancy that you're getting back at this stage, is really going to influence the quality of the system as a whole. So now I can take those top similar lines and just embed them into the actual modified query that I'm going to send along to the actual model. So I might rephrase that original query to say, you are Commander Data from Star Trek. How might Data respond to the question, Data, tell me about your daughter Lal, taking into account the following related lines from Data? And then I would proceed to paste in the list of the top 10 similar lines that I found from my vector database there. And when I feed that in turn into the chat completions API for OpenAI or whatever model you're using, I will get back a response that hopefully takes those external results into account. And we can go and try it out. So again, that final prompt that we're creating in RAG is going to be a combination of the original query, the prompt template that we're using, and any relevant data that we extracted from the retrieval stage of RAG. That's all there is to it, folks. So let's go and actually build this thing now and see if it works. All right, so let's walk through an example of using retrieval augmented generation to do that same thing we did with fine-tuning earlier, to actually recreate the character of Data from Star Trek, only this time through cheating. So again, the high-level approach here is that we're going to parse all of the scripts from every episode of The Next Generation to extract every line that Data ever said in the TV show. Very much like we did in the fine-tuning example. The difference, though, is that we're not going to take into account the context of who Data was talking to. We're just going to extract his individual lines, because we're just going to be searching against them here. After that, we're going to use the OpenAI embeddings API to compute embedding vectors for every one of those lines, and then we'll shove those all into a vector database. And to keep things simple, we're going to use something called Vector DB, which just runs locally in your little environment here. So rather than making you go sign up for yet another cloud service and yet another cloud-based database, we're just going to do this locally using Vector DB. Obviously, in the real world, you might want to use something more robust. Once we do that, we're going to make a little retrieval function for RAG, and its job will be to retrieve the n most similar lines from the vector database for a given query. So when we're going to ask Data a question, I'm going to go hit that vector database to retrieve the most relevant lines of dialogue associated with that query. Once I get those back, I'm just going to add them as context into the prompt before I hand that off to chat completions to get back an answer from OpenAI. A quick note here about LangChain. So a lot of the examples you see for retrieval augmented generation use a higher level framework called LangChain, and it's pretty popular right now. I'm not using it here, A, because I don't know if it's going to stand the test of time or not, but B, you don't really need it. I mean, this is not complicated stuff. So yes, LangChain might save you a few lines of code here, but not enough to be worthwhile. I think it's more important to understand how to do this from scratch to understand what's going on. All right, so let's dive in. So before we do this, there's a couple of bits of housekeeping we need to do. First of all, later on, we're going to need to actually retrieve those script files. So to do that, I need to go to my files section here in CoLab. And by the way, I do recommend using CoLab for this, mostly because VectorDB has a lot of weird dependencies, and something like Anaconda locally, you're probably going to run into installation problems with it. Even CoLab has trouble with it, but it works at least for now. Anyway, let's upload those script files before we forget. Open up the sample data here under your files, and we're going to create a new folder. New folder. And we're going to call that TNG. for the next generation. And there, we're going to upload our scripts. Now, just a reminder where to get them. Let me cancel out of this. So there's a little handy dandy link here. I can't include this with the course because it's copyrighted, but if you want to go and get these, I can't stop you, right? So you want to look for the all TNG episodes archive here. That's what we're using. And again, you could use this with any TV show or movie that you like. I mean, most scripts are pretty similar in format. But I already did that, so I'm going to go ahead and upload those into my new TNG folder. So let's say upload, and I'll navigate to where I downloaded that to. Scripts TNG, and I'm just going to select everything here and throw it in. So we're going, yeah, I know they're not going to last. Well, let's wait for that to upload. Meanwhile, the other thing we need to do is put our OpenAI secret key in here so we can access that as well, because we're going to be using the OpenAI API to generate embedding vectors and also to do our chat completion. So under the little secrets tab here, what I want you to do is say that your notebook access should be on. You want to give it a name of OpenAI underscore API underscore key, and then paste in your secret key from OpenAI. And if you need to go get that from your OpenAI account, go take care of that first. All right, that's all we need to do to prepare. So let's go back to our files here. Looks like those are all uploaded. Cool, we're ready to rock and roll. All right, so let's get started. First thing we're going to do is install the VectorDB package. So go ahead and shift enter on that, just pip install VectorDB. And if you're doing that the first time, that will probably take several minutes. So go ahead and pause this video and come back when you're done. All right, as promised, that took a few minutes, and there are some scary looking errors. They should be safe to ignore though. Moving on. So let's start by parsing out those scripts and extracting the data that we need. This is very, very similar to the code that we looked at in our fine-tuning exercise, so I'm not going to spend a lot of time on it. But again, at a high level, all we're trying to do is find the lines of dialog the data set. And the raw script files here are in kind of an unfriendly format. So you tend to see that the format is basically, you'll see a line of text that has a single all caps name in it. We're going to use that as a signal that somebody's about to say something and who's about to say it. So essentially, I'm going through this and looking for single lines that just say data in all uppercase. Let's see if I can find one here real quick. Yeah, like data. It registers as solid, Captain, right? So all this code is going to do is go through here looking for lines that say data, and then taking the next series of lines until we see an empty line and say, okay, that's going to be that line of data, and reformat it to be, a single sentence on a single line, right? So that's all that's going on here, really. So we have all this stuff to like strip parentheses from things and test if something is a single word in all caps, which means it's probably somebody's name, and then extract those subsequent lines of dialogue until we hit a new line to get that one line of data. And here you can see where we're hard coding that we're looking specifically for data. There are more elegant ways of coding that for sure. This process directory function just goes through every single one of those files that we uploaded. These all represent an individual script from an individual TV show, and goes through each one of them and extracts everything the data ever said. And it puts all of those into an array called dialogues. So that we're going to have this array called dialogues that just contains everything data ever said in that TV show. All right, we kick that off. Let's go ahead and shift enter to get that in there. And now we're going to actually call it with the process directory call. And it shouldn't take too long. Already done. Pretty easy, right? Let's go ahead and make sure it actually worked. So let's just print out the first line of dialogue that it extracted to make sure something's there. And it is. So, the first line of dialogue in this example was Ambassador Odon, Dr. Crusher, I was just on my way to see you. And based on the order that things uploaded here, your line there might be different than mine. Don't worry about it. All right, so now let's set up our vector database. All we need to do is import what we need from it. So we need something called basedoc and also NDArray to construct basically the class that defines what a document in our vector database looks like. It's very simple for us. It's just a string, that's the line of dialogue, and the embedding vector, which is an array of however many dimensions we choose. Now, just to keep things simple and fast, I'm going to choose 128 embedding dimensions here. You could go larger though. I believe the model we're using has up to 1,536. So you could play around with that and see if your results get better as a result. But let's stick with 128 for now. Go ahead and run that. Might take a little bit of time since it has to import some stuff for the first time here. And that's done. All right. So Next thing we have to do is compute the embedding vectors for every one of those lines of dialogue before we insert it into our vector database. So let's start by installing OpenAI. That's just the OpenAI API. And that's done. Again, we should be okay with those errors. We'll find out the hard way soon. All right, so now what we're going to do is actually use the OpenAI client and say, let's make an embedding. At this point, we're just going to test and make sure that it works with a single line of dialogue here. So what I'm going to do is create the OpenAI client here. We're going to construct that using the OpenAI API key. Again, you already put that into your secrets, right? If not, go take care of that now. We'll choose our embedding model, text embedding 3 small. Over time, these models do change and get deprecated. So if that stops working for you, just use a newer model. You'll be fine. And just to see if it works, let's go ahead and create an embedding vector from the second line of dialogue that we have, whatever that is, with 128 dimensions, and using the embedding model that we specify and print out the results. Let's see what we got. It worked. Awesome. So we got back a vector, hopefully with 128 dimensions. Let's double check. Just print the length of that vector. It is indeed 128. All right, so we appear to have a means of creating embedding vectors for given lines of dialogue. Cool. So now let's do that en masse. We're going to create a new list called embeddings that contains embeddings for every single line that data ever said. And because you can only do this in a batch up to a certain point, I'm going to do this 128 lines at a time. So using a little bit of Python trickery here to say that I'm going to be going through every line of dialogue that I have, which is in the thousands, and go through it 128 lines at a time. So for every chunk of 128, I'm going to feed that to the OpenAI client and create a bunch of embeddings all at once by passing in that slice from our total array of dialogues 128 at a time. So the input here does not have to be a single line of dialogue. It can actually be an array, and that works too. So in this case, we're taking something called dialogue slice, which is just a slice of 128 lines. And we do that over and over and over again until we get through everything. And as we do that, we keep on adding the results to this embeddings list that we're building up. So let's go ahead and do that. And you might think this would be expensive and take a long time, but it doesn't. Like I said, this costs less than a penny, at least today. And you'll see it's done pretty quick, considering that it's encoding over 6,000 lines of dialogue here. So let's just wait for that to finish. And we're done. And you can see that took less than a minute. That might seem like a while, but compare that to how long it took us to fine tune the model using that same data. That took hours, right? So you can see this is a lot faster and cheaper than fine tuning. But, you know, again, it's cheating and the results will reflect that. You know, it can't actually, it's not really building a model of how data thinks and talks per se, right? It's just going to be regurgitating these lines of dialogue that we gave it to some extent. Let's just make sure that we got back as many embeddings as we expect. How many did we get back altogether? 6,502. Hopefully that checks out for you as well. So now let's go ahead and insert those into our vector database, into VectorDB. Pretty simple to do. We do need to create a workspace directory though. So back to my sample data here, let's go ahead and create a new folder again. And I'm going to call that workspace because we need to store this vector database somewhere. So all we're going to do is say that we're going to create a new VectorDB using the in-memory exact NNV VectorDB implementation, using that directory for its files. Okay, then we just, in this one line of magic Python code, we go through every single embedding and we go ahead and insert it using dialog line with the associated line of dialogue and the associated embedding vector for that line. And we just index it when we're done. So let's kick it off. And that was unbelievably fast. I hope it really worked. We're about to find out. So let's test it out. Let's actually do a query here, and we'll query the text lol my daughter. We'll go into OpenAI and create an embedding vector for that query, and then query our database, our vector database, to get the top 10 most similar lines of dialogue to that query. So we construct a query that consists of the query text lol my daughter, the embedding vector that we got back from OpenAI, and we do a search with a limit of 10 results, and we print them out. Let's see what happens. And it worked. My gosh, it really was that fast in inserting all that data. Let's scroll up and see what we got back. All right, so the first line of dialogue that came back was the line, "That is lol my daughter," which is a pretty darn good match to lol my daughter. So that's a pretty good indication that the vector database is working as intended, that these embeddings really are positioning these lines of dialogue together based on their similarity to each other. And then we got some more stuff too. So at one point you just said, lol. Well, that's not going to be terribly helpful. What do you feel, lol? Again, probably not very helpful in constructing the response. Yes, lol, I am here. Correct, lol, we are a family. I guess the underlying model might pick up something from that. No, lol, this is a flower. Maybe that's telling the model that, hey, lol has trouble recognizing things. Lol used a verbal contraction. So this is giving us more and more information about Data's daughter, lol. And just to give you the backstory here, in case you don't know, which you probably don't because you're not a nerd like I am, in one episode, Data, who was an android in Star Trek The Next Generation, constructed a daughter for himself, who was also an android. And, well, things happened. Yes, Wesley, lol is my child. Apparently we know that Data talked to Wesley Crusher about it, and now we're getting something a little bit more meat to it. Lol's creation is entirely dependent on me. I'm giving it the knowledge and skills that are stored in my brain, so on and so on. So by combining all of these different lines that are about Data's daughter, lol, maybe we can give the underlying model something to work with to give it a more relevant response when I ask it about lol. All right, moving on. So let's put it all together and actually wrap this all up. So I'm going to write a generate response function here, and its job is just to compute an embedding for any arbitrary query that's passed in. It will go and query that vector database for the 10 most similar lines, just like we did, and you might experiment with using more or less results. Again, you have to draw that line between relevancy, right? Too many will give you irrelevant results. Too few might not give you enough information. Balancing that is a bit of an art. And then we'll construct a new prompt that adds in those similar lines as context to try and nudge ChatGPT in the right direction using that external data. We'll then feed that augmented prompt into the chat completions API to get a response that takes that database, that vector database data into account. So we take the question, we create embeddings for it, right? We take that embedding and create a query out of it and then search the vector database for the top 10 most relevant lines of dialogue to that query. That's just what we did before. We will then extract relevant context from the search results. So I'm going to go ahead and go through every one of those matches that come back and add that to a string that's just putting each line that came back on its own unique line. And then I'm going to append that in here. So that's going into a variable called context, okay? So question is the original query. Context is the additional context I'm going to pass in as part of that query. And the prompt here that I'm going to use is Lieutenant Commander Data is asked, whatever the question was that was passed in. How might Data respond? Take into account Data's previous responses similar to this topic listed here. And then I'll give it that list of the top 10 most relevant lines from the vector DB. Then I'll print out what that modified prompt looks like so we can look at it, send it off to chat completions, and get the response back. And just to help it out a little bit further, we'll give it a system prompt that says, you are Lieutenant Commander Data from Star Trek The Next Generation. Hopefully that will give the system some cues to use the underlying knowledge that it already has about that character that it was trained on, but take this new data into account as well. And we'll print out the results that we get. All right, let's kick it off. So that's just generating the generate response function here. Let's now use it, and we can pass in a question like, tell me about your daughter, lol. All right, and so remember the prompts that we gave it, right? So we're going to give it the top 10 most relevant lines of dialogue it could come up with here. So given tell me about your daughter, lol, the vector DB came back with these lines of dialogue. This is lol, my daughter. How do you feel? Lol, we are a family. Yes, daughter is an experience I know too well, but I do not know how to help her. Lol is passing into sentience. This is a difficult stage of development for her. She's not the same as other children. She is my child. Talking to Wesley. Something happened to her at school. She talked to Counselor Deanna Troy, right? So maybe the captain wants him to deactivate lol. And it's going to put that all into the modified query here that we're seeing here. So Lieutenant Commander Data is asked, tell me about your daughter, lol. How might Data respond? Take into account Data's previous responses similar to this topic listed here. Okay, so that's our modified prompt where we used RAG to augment that prompt with external information. And the response we get back isn't bad. So there are actually several that it gave us to choose from here. Data would likely respond to the question about his daughter, lol, in a logical and straightforward manner. He would provide information. Yeah. So, for example, he might say, lol is an android constructed by myself. She was created using a positronic neural network, blah, blah, blah. Although she was designed as an advanced prototype, she is itself involved into a sentient being. So that might be picking up on the sentience bit that we fed to it. Lol has exhibited various experiences and challenges in her development. Okay, so, that was definitely referred to in these lines that we gave it as well. The journey towards sentience. seeking guidance from others, such as Counselor Deanna Troy. That's definitely coming directly from the data that we gave it. So you can see it's taking that information that we gave it into account and using that to sort of augment, hence the A in RAG, the response that it would have given us back without that information. So it's made the response better. The whole point of retrieval augmented generation is to augment your model with external data that may be proprietary, that may be more recent, that the model didn't have originally. Or maybe you just want to nudge it in a certain direction based on that external database lookup. But you can see it's not complicated, right? So none of this was hard. None of it's particularly resource intensive. So you can see how this is a very attractive approach for people that want to incorporate their own data into their generative AI systems. The results can be mixed. Again, it depends a lot on the relevancy of your results. If you look at the results that we got back here, a lot of them aren't giving us a lot of information, right? Like the line that just says lol, that's not doing me any good, right? So again, it's only going to be as good as the data that you're getting back from that database. But that's an end-to-end example of using retrieval augmented generation. Again, recreating the character Lieutenant Commander data from Star Trek using AI and RAG in this instance. Is it better than fine-tuning? I'll let you be the judge. I don't think so. I think the fine-tuning results were more interesting, but again, it came at a much higher cost and it took a lot more time to do it. So sometimes you got to weigh those things off and trade things off, right?